Welcome back to the Deep Dive. We're here to cut through the complexity and get you the insights you need. And today, well, we've got something really important, especially if you're gearing up for a career in welding inspection. This is actually a special installment focused on the CSWIP 3.1 exam prep. We're aiming to help you tackle some of those multi-choice questions that often pop up on the Welding Inspector Exam. Yeah, the goal isn't just giving you answers. We want to dig into the why behind them so you really understand the principles. Think of it as a way to get informed fast, packed with stuff you can actually use on the job, not just for the test. Okay, let's jump right in, shall we? First up, a fundamental one about MMA welding, that's manual metal arc. It's about penetration. So the question is, which of the following under typical conditions using the MMA welding process would give the deepest penetration? Your options: A, DC negative, B, DC positive, C, ACD. Yeah. Both A and B. Have a quick think. Which one really digs deep?
Right. This one often trips people up initially. The answer is B, DC positive.
DC positive. Oh. Okay, why is that?
Well, with DC electrode positive, or DCEP, your electrode's on the positive terminal. The electrons, they flow mainly from the workpiece to the electrode. What this means is about 2/3 of the arc heat gets concentrated right there on the base metal.
Ah, so the workpiece gets hotter.
Exactly. That focused heat is what gives you that deeper, sort of narrower penetration profile. Really important for things like root passes or thicker materials where you need that good fusion.
Okay, that makes sense. So here's where it gets really interesting for you as a future inspector, knowing this helps you predict things, right?
Yeah.
You can look at a weld profile and have an idea of what might be going on. Like if the WPS calls for DCEP for a thick plate, but the bead looks wide and shallow, what should you be thinking?
That's a huge red flag immediately.
Right.
It strongly suggests either the parameters, amps, volts, travel speed were off, or, and this is quite possible, they might have used the wrong polarity, like DC negative. Yeah, DCEN. With DCEN, the heat's focused more on the electrode, so the electrode melts faster and you get a wider, shallower pool on the workpiece. That difference in bead shape, it's often one of the first visual clues you'll get. It shows why inspectors need to know this stuff, not just the welders. You're making observations, diagnosing potential issues.
That's practical foresight, turning theory into a tool. Excellent. Okay, we've talked about getting the weld profile right, but what about internal issues? Let's talk solidification cracking, a really common critical defect. So our next question, which of the following can be used to reduce the chances of solidification cracking? Options are A, using a non-flux process and better quality materials. B, better quality materials and the highest heat input process. C, using a low dilution process and wider joint preparation. D, adding silicon and using a low hydrogen process.
Okay, for reducing solidification cracking in this context, the best approach listed is C, a low dilution process and wider joint preparation.
Low dilution and wider prep. Let's break that down. What exactly is solidification cracking?
It's often called hot cracking. It happens right as the weld metal is solidifying. Think of it like this. As the metal freezes, impurities like sulfur or phosphorus get pushed into the last bits of liquid between the solidifying grains. These liquid films at the grain boundaries are weak points. Then, as the weld shrinks during cooling, these weak spots can just tear open under the stress.
Like pulling apart something that's not quite set yet.
Precisely. Now, a low dilution process helps because it means less mixing of the base metal, which might contain those impurities, into the weld pool. You control the weld metal chemistry better.
Keeping the bad stuff out, essentially.
Yes, and the wider joint preparation. That creates a larger weld pool, often with a more convex shape as it solidifies. This wider shape helps spread out the shrinkage stresses and can encourage a grain structure that's less prone to cracking as it cools down.
So it's about making smart choices upfront process and joint design, not just fixing cracks later. Could you give an example? When might an inspector spot a high dilution risk before welding starts?
Sure. A classic example might be trying to weld, say, a thin piece onto a much thicker base metal known to have high sulfur content. Maybe using a high penetration process like submerged arc welding.
Right. That sounds like asking for trouble.
It is. An inspector reviewing the WPS should flag that. They might suggest a different process, maybe a specific filler metal, or even applying a buttering layer first to isolate the weld from the base metal.
And the wider joint prep, what does that look like?
We're talking about things like a wider V-groove angle, or maybe using a U-groove or J-groove. These provide more volume for the weld metal, allows for multiple, often smaller passes. It creates a larger, more robust pool shape, especially at the root, giving those impurities less chance to concentrate and cause trouble. It's about engineering the solution.
Got it. Engineering the solution. I like that. Okay, let's move into seeing inside the weld. Non-destructive testing, specifically radiographic testing. Our next question needs you to pick the correct statement about radiographic indications. Listen closely. A, on a radiograph, slag inclusions and copper inclusion would both show up as light indications. B, on a radiograph, tungsten inclusions and excessive root penetration would both show up as light indications. C, on a radiograph, cap undercut and root piping would both show up as light indications. D, on a radiograph, excessive cap height and incomplete root penetration would both show up as dark indications.
All right, the correct statement here is B. On a radiograph, tungsten inclusions and excessive root penetration would both show up as light indications.
Light indications. Why is that?
It comes down to how radiography works fundamentally. You pass X-rays or gamma rays through the weld. Areas that are denser or thicker absorb more radiation.
Yeah.
Less radiation gets to the film or detector behind it, so those areas look lighter on the radiograph image.
Okay, denser or thicker means lighter image.
Exactly. And areas that are less dense or thinner, like porosity or lack of fusion, let more radiation through, appearing darker. So tungsten. It's a very dense metal, much denser than steel. It absorbs a lot of radiation, shows up light. And excessive root penetration. That means extra weld metal sticking through, making that section locally thicker, more thickness, more absorption, so it also appears light.
That's a key principle. But let's say you, as the inspector, see a light spot. Besides tungsten or excess root, what else could it be? How do you tell them apart?
That's a great question because interpretation takes skill and experience. Other dense things, maybe lead contamination, though less common, could also be light. The key isn't just light or dark, it's the shape, the size, the location, the sharpness of the indication.
The characteristics.
Precisely. A tungsten inclusion often looks angular, irregular. Excessive root penetration follows the root line, looks like extra weld bead, usually smoother. You compare what you see to reference radiographs, consider the welding process used. It's like being a detective, really, analyzing the clues on the film. Training and practice are essential.
Right, reading the story the radiograph tells. Okay,
Yeah.
Let's shift focus slightly now to preparation and safety. Degreasing agents. Essential for clean welds, but they can have hidden dangers. The question is, degreasing agents used on components are essential for quality welding. During and after welding, some agents may. Options A, cause corrosion problems. B, leave residues. C, give off toxic gases. D, all of the above.
Okay, while A and B can definitely be issues for weld quality, the most critical hazard here, the one we absolutely need to be aware of from a safety standpoint, is C, give off toxic gases.
Toxic gases, that sounds serious.
It is extremely serious. This is something that cannot be emphasized enough. Certain degreasers, especially older types containing chlorinated hydrocarbons, think trichloroethylene, perchloric ethylene, can break down under the intense heat of the welding arc. When they decompose, they can form phosgene gas.
Phosgene, isn't that like chemical warfare stuff?
It was used as such, yes.
Okay.
It's highly toxic, colorless, maybe a faint smell like cut hay at higher concentrations, but dangerous even when you can't smell it. It attacks the lungs, and the symptoms can be delayed, which makes it incredibly dangerous. People might feel fine initially and then become severely ill hours later.
Wow.
This is why proper ventilation and, effective local exhaust ventilation right at the source is absolutely critical if there's any chance these solvents were used. And honestly, the best practice is to just use safer, non-chlorinated alternatives altogether. Don't take the risk.
That's a vital safety point. So, as an inspector, if I walk onto a site and I suspect maybe chlorinated degreasers were used, what should I do beyond just checking the general ventilation?
Good question. First, find out exactly what was used. Check the MSDS, the Material Safety Data Sheet.
Right.
If it confirms chlorinated solvents, work involving heating, that component needs to stop immediately until the hazard is properly controlled. That might mean specific local exhaust, maybe even air monitoring. General shop ventilation often isn't enough, and welders might need specific respiratory protection. Your job as an inspector often includes ensuring the work environment is safe, not just checking the final weld. It's part of the overall quality picture.
Absolutely. Safety first. Okay, for a final question, let's get into calculations. We're looking at arc energy, or heat input, a key parameter for controlling weld quality. The question, which is the correct arc energy for the following parameters? Amps 350, volts 32, and the travel speed 310 millimeter MA welding process. Your options are A, 2.16 kilojoule millimeter, B, 0.036 kilojoule millimeter, C, 21.6 kilojoule millimeter, D, time for a bit of math.
The correct answer here is A, 2.16 kilojoule millimeter.
2.16, how do we get there?
There's a standard formula for arc energy or heat input. It's heat input in kilojoules per millimeter equals voltage times amperage times 60, all divided by travel speed in millimeters per minute times 1,000.
Okay, V times A times 60 divided by speed times 1,000. Why the 60 and 1,000?
The 60 converts the travel speed from per minute to per second because volts times amps gives joules per second, watts. And the 1,000 converts the result from joules per millimeter to the more common unit of kilojoules per millimeter.
Got it. Units matter.
They absolutely do. So plugging in the numbers. 32 volts, 350 amps, 60, 310 millimeter and 1,000. That's 672,000 divided by 310,000, which comes out to about 2.1677. So rounding it gives us 2.16 kilojoule a meter.
Right. And why is knowing this number, this arc energy, so important?
It's critical because it directly impacts the cooling rate of the weld, which in turn affects the microstructure, the grain size, and the final mechanical properties like strength and toughness. Too much heat input, things cool slowly, you might get large grains, lower toughness, maybe more distortion. Too little heat input, things cool too fast, you might risk lack of fusion, poor penetration, or even cracking in some materials. It's about finding that right balance specified in the WPS.
So this number isn't just academic. It really controls the weld's properties.
Yeah.
How does an inspector check this on site? You're not usually doing the math constantly, are you?
No, not usually calculating on the fly. But you are verifying the inputs to the calculation.
Checking the parameters.
Exactly. You check if the welding machine is calibrated, observe the welder's travel speed to see if it's consistent and matches the WPS range, and confirm the voltage and amperage settings are correct.
And what if they're slightly off? What are the consequences?
Even slight deviations outside the qualified range specified in the WPS can be significant. Consistently high heat input might lead to a larger heat-affected zone, potentially failing toughness tests later. Consistently low could mean you're not getting enough penetration, which is a major defect. The consequence could be needing immediate correction, maybe retraining or requalifying the welder, or costly repairs to welds that don't meet the standard. It's all about process control for quality and safety.
Process control. That sums it up nicely. And just like that, we've covered some really vital ground for anyone heading towards their CSWIP 3.1 exam or just wanting to be a better inspector. We looked at penetration in MMA, how to reduce solidification cracking, reading radiographs, the crucial safety aspects of degreasers, and calculating arc energy. It's a lot, but it's foundational.
It really is. And what's interesting is how it all connects, Electrical principles, metallurgy, safety, procedure control, it all comes together for weld quality. My advice, as you study, is always ask why. Don't just memorize the answer. Understand the reason behind it and how you'd apply it practically. That's what makes a truly effective inspector.
Couldn't agree more. Understanding the why. So here's something to think about. We've covered these core principles, but what about situations or maybe newer processes where these rules might have nuances or even exceptions? What else could impact weld integrity that we haven't touched on today? Something for you to consider. Thanks for joining us on this deep dive. Keep studying, keep questioning, and good luck with your preparations. We'll catch you next time.